Hello everyone. So today I'm going to give a presentation on sparse matrices, what they are, why they matter, and how they can be implemented using different techniques in programming. So my name is Ritika Paul, and here today I'm representing this presentation, presenting this presentation. So this is the basic introduction of a matrix. A matrix is just a table or a grid of numbers arranged in rows and columns, and I have already given an example. And it's basically a 3 rows and 3 column. And so this whole presentation is about a sparse matrix. So how a sparse matrix is different from a normal matrix. So in a sparse matrix, it have a lot of zero elements, the example. Like I have already given the example, it have very few non-zero elements, mostly zeros. So the objectives are they save memory because we store only the non-zero elements, faster calculation since we can skip the zero part. Storing all the values like including zeros waste both time and space, enables efficient algorithm, like it enables efficient algorithm design for larger linear systems. And it can also help in the real life problems like the graphs, recommendation systems, and natural language processing finite element analysis, where data naturally form a sparse structure. So there are two types in which we can store matrix. So that is array representation and linked list representation. So first we are talking about array representation. So in array representation, we store only the non-zero elements using a 2D array and a 2D array with 3 rows. Each columns store row index of the non-zero value, column index, actual value. This avoids the storing zero and saves memory. Basically, this method is best when the matrix size is fixed and doesn't change often. Now, let's come to the code part. So this is basically, we are starting with a basically header file, which will allow us to support different output commands later, like printf. So here we defined a constant max with a value of 100, which means we can store up to 100 non-zero elements in our array. First, we are initializing. First, we are making, we define a struct called element, which is used to store each non-zero value of the matrix. And we are initializing row number, column number, and the actual value. In the main function, we first define a 3x3 matrix named sparse, which contain mostly zero and a couple of non-zero values as just a second. Yeah. And couple of non-zero values. This is and couple of non-zero values. This is our example of a matrix, sparse matrix example. Now moving on, then what's happening is then we create an array elements to store the non-zero elements of the matrix using our element structure. We also initialize k to 0. This will help us to track of how many non-zero elements we have stored. Next slide. So now we started a nested loop to go through every element in the matrix. We print each element as we go, so we can see the full matrix printed row-wise. Now, inside this loop, so now first we created this loop, and inside this loop, what's happening is if the current element is not 0, that means it's not important. So we store its row, column, and value in the elements array. Then we increment k to move to the next position in the array. After printing each row of the matrix, we move to the next line using \n. Once we have stored all the non-zero values, we now print the final sparse matrix representation. We label the columns as row, columns, and value. These loops print each non-zero element in a clean format. It shows the position, row, column, and the actual value of the matrix. Finally, we return 0 to indicate the successful program execution. So now this is the output. So we're basically entering the number of rows, columns, and the elements we want to add in our matrix, and the computer will give us the required matrix. Now, I would like to conclude this array representation a bit. So what we did first is we first created a matrix with mostly zero values. Then we used a structure to store only the non-zero elements. We printed both the original matrix and the compressed sparse representation. So this is a very simple and memory efficient way to work with the sparse matrices when we know that most of the values are going to be zero. So now let's move to the linked list representation. So linked list representation have nodes in it. This is a more dynamic method. Each node stores row, column, value. It saves only important data, non-zero values. A pointer more flexible than array, we can say, allows dynamic change. While in array representation, it doesn't allow us to explore that much, but in linked list representation, since it allows dynamic change, we can explore this code a bit, and we can use it in different ways. And it saves memory by storing all important data, useful for dynamic or changing sparse matrices. This is especially helpful in the graphs where the data keeps changing. So now we are going to the code part. So again, we are starting with the header file. This is our node structure. So the first struct node is first we're initializing row, column, value, and a pointer to the next node in the list. Then we are creating and inserting a node. We are creating a new node. So here we create new nodes with create node and insert node. Here create nodes dynamically allocates some memory and fills in the row, column, and value. Row, column, and value. Insert node adds the new node at the end of the list. And the header pointer keeps track of the start of the list. Now, here, so if the linked list is empty, we directly set head to the new node. Otherwise, we go to the last node and link the new node there. Just a second, I'm having some trouble with this slide. Yes. Yeah. So yeah, this is what I was talking about. If the linked list is empty, we directly set head to the new node. Otherwise, we go to the last node and link the new node here. Now, this function basically void display. Yeah. So this function basically here, the function to display the linked list. So this function prints the linked list in a table format showing row, column, and value of each non-zero element. Now, after this, we gave the code a 3x3 matrix. As we can see, there are only two non-zero elements, that is 5 and 8. Now, we loop through the matrix, and if we find a non-zero value, we insert it to the linked list using the insert node function. Okay, wait just a second. To summarize this, yeah, I would like to summarize this now. To summarize this, we first did a sparse matrix that has mostly zero elements. Using a linked list, we store only non-zero elements along with their row and column position. This method saves memory and improves efficiency for larger matrices with very few non-zero values. Yeah, so that was it. And yeah, I explained this part. And then we, of course, return zero. So to, ensure a successful code execution. So this is the output. This is the output. This is a basic, simple output. Now, so here the conclusion is sparse matrices are great when there are a lots of zeros. Two simple ways to represent them is array and linked list. Easy to use in real world problems like graphs where the data is constantly changing, search engines, etc. Their main advantage lies in saving money and computational resources by processing the non-zero elements. The yeah, and processing the only useful data, you can say. So yeah, this is it. And with this, I'm concluding this presentation. Thank you very much.